Cherenkov radiation is a bluish violet electromagnetic radiation produced by charged particles in motion when they pass through an optically transparent medium with a velocity greater than the phase velocity of light. We know that in free space no velocity can exceed velocity of light, and therefore Cherenkov radiation is absent in free space. The refractive index of the medium in which such a radiation is produced must be greater than unity, such that C upon eta is less than C. This phenomena is similar in nature to shock waves of sound produced by moving objects with supersonic velocities. Certain devices sensitive to Cherenkov radiation, called Cherenkov detectors, have been extensively used to detect the presence of charged subatomic particles moving at high velocities. Depending on the velocity of the charged particle in a dielectric medium, polarization pattern changes. When the charged particle is moving slowly, the polarization pattern is completely symmetric. An electric field of charged particle is screened by the polarization effects. When the particle is moving very fast so that velocity of the charged particle is greater than the phase velocity of light in that medium, then the electric field is seen at large distances because the polarization pattern changes. Here we have a cylindrical coordinate system. When the charged particle is moving at very high velocities, the atoms have azimuthal symmetry, but they do not have the axial symmetry. If we look at the cylinder, this is the azimuthal angle theta. That means the polarization is symmetric when we increase theta, but the polarization is not same when we move along the axis. If we look at this picture, the polarization is same if we go by the azimuthal angle, but the polarization is different when we go by this axis. That means the polarization pattern is different in front and in the back side of the charged particle. And in this case, there is electric field seen at large distances. In the cylindrical coordinates, we have rho, z and theta. Rho is the radial direction in cylindrical coordinates, theta is the azimuthal coordinate, and z is the axis of the cylinder. That means we have two electric fields components, two components of the electric field, one along the z direction, another along the rho direction. In case where the velocity of the charged particle is higher than the phase velocity of light, it is possible for wavelets from all portions of the track to be in phase with one another, so that a wavefront is formed at a particular angle theta with respect to the velocity vector of the charged particle. This is a very particular angle. It can be understood using Huygens construction. Radiation is seen only at a particular angle theta with respect to the track of the particle. Coherence of wavelets from all portions of the track takes place when a charged particle traverses A to D in a time while the light travels from A to M. So if we look at this picture, the time taken by the charged particle to reach D from A is the same as the time taken by light to reach M from A. That means we have a right angle triangle here. Now from physics we can substitute the values of AM and AD. AD is beta into C multiplied by tau, and AM is C by eta multiplied by tau. That means delta tau cancels, and cos theta is 1 upon beta eta. So this angle of emission is the angle of emission of the Cherenkov radiation. There are three properties from this relation that we can straight away infer from this relation. Number one, there is a minimum value of beta, which is 1 upon eta, which is obtained when cos theta equal to 1. In the ultra-relativistic limit, we can have maximum velocity of the charged particle when beta equal to 1, then theta max equal to cos inverse 1 upon eta. That is property number 2. And property number 3 is that eta must be greater than 1. That means the emission is in the visible or near visible regions of the spectrum. When eta is greater than 1, that means in the X-ray region the emission will not be seen. What happens for V less than C by eta? That means the velocity of the charged particle is less than the phase velocity of light. We can look at this picture. Here the particle has moved this much V into T in the time when the wavelets have reached here. That means the particle is within the wavelet emitted by itself. That means the emitted wavelets remain within previously emitted wavelets, and a common tangent cannot be drawn. A wavefront cannot be constructed using Huygens principle. That means we cannot expect to get Cherenkov radiation when velocity is less than C by eta. What happens in 3 dimensions? First look at the 2-dimension picture. This is the track of the charged particle. This is the direction in which the radiation is going. But in 3 dimensions, if you translate this figure into 3 dimensions, it will look like a cone. And here is the theta, and this is the surface of the cone. Electric field E is perpendicular to the surface of the cone, and magnetic field is tangential to this ring. That is electric field and magnetic field. And if you break this electric field, then you will get 2 components. Electric field is perpendicular to the surface of the cone, so it goes perpendicular to the surface of the cone, and so it has 2 components, Ez and E rho. So that is the cylindrical in the cylindrical coordinates in the picture that we saw before, that the electric field has 2 components, one along the Z direction, another along the rho direction. Two more conditions. Length L of the track of the particle in the medium should be large compared to the wavelength lambda of radiation. Otherwise, we will observe diffraction effects. That is condition number 1. Otherwise, we will observe diffraction effects. Light will be distributed along delta theta in a small angle, lambda by L sin theta, instead of appearing only at one angle theta. That means the length of the track of the charged particle has to be larger than the wavelength of radiation. And second condition, means second extra condition, is that the velocity of the charged particle must be constant during its passage through the medium. Specifically, the difference in times for the charged particle to traverse successive lambda distances should be small compared to the time interval lambda by c. Now we look at the theory of Tam and Frank. Theory of Tam and Frank, developed in 1937, got Nobel Prize in 1958, predicts the number of photons emitted in the frequency range nu to nu plus d nu, emitted by a charged particle of charge Ze and velocity v equal to beta multiplied by c in a medium of refractive index eta. This is the frequency distribution according to the theory of Tam and Frank. That means n nu d nu depends quadratically on z, that is on z square. It depends on eta and depends on beta in this form. We can infer several points from this expression of photon distribution function of Cherenkov radiation. For example, we can explain the origin of its bluish violet color. The spectrum is identical for particles of same charge. For higher charge, n nu increases as z square. N nu increases with velocity. It is 0 when beta equal to 1 over eta, and its maximum value reaches when beta equal to 1. N nu d nu is independent of nu. This is very important, and this will give us the bluish violet color. And number 5, to get appreciable intensity of light, one has to choose a medium of high refractive index. This also follows from the theory of Tam and Frank. Let us examine closely point number 4. This means that since the photon energy is equal to h nu, there is a greater energy concentration of high frequency radiation in the spectrum, which explains the preponderance of bluish violet color of emitted Cherenkov radiation. What is the difference between Cherenkov radiation and Bremsstrahlung? Bremsstrahlung is electrons beamed at a metal target in a X-ray tube are brought to rest by head-on collision with the nuclei. That means here the charged particle has to come to rest when it emits the radiation, but in Cherenkov radiation the charged particle has to have a constant velocity to emit Cherenkov radiation. That is the basic difference, Cherenkov radiation and Bremsstrahlung. Now let us look at the atmospheric muon neutrinos. Atmospheric neutrinos are typically produced around 15 kilometers above Earth's surface. They form when a cosmic ray is mainly a proton, a high energy particle from space, enters Earth's atmosphere. These particles are typically protons, though they can also be helium or heavier nuclei. When they strike an atomic nucleus in upper atmosphere, there is a cascade of particles consisting of mesons. Most of them are pi mesons. So we can look at this picture. Here is a cosmic ray coming from deep space. It comes to our atmosphere and strikes an atom, and it is a high energy particle, so it can interact with the nucleus. So after interacting with the nucleus, it produces pi mesons, and pi mesons decay into muons and muon neutrinos, and muons furthermore decays to electrons, electron neutrino and muon neutrino. That means for each pion we get 2 muon neutrinos and 1 electron neutrino. Muon neutrino anomaly refers to the observation that atmospheric muon neutrino flux is substantially lower than the expected value. What is expected value? In detailed computer simulation of expected events, we obtain the ratio, theoretical ratio, R theory, equal to n mu by Ne approximately 2. And finally, experimentally, we get R observed, that means this ratio, observed ratio by expected ratio, R observed by R theory, 0.54 to 0.57. It's not 1. That means muon neutrinos oscillate to electron neutrinos or to tau neutrinos. Nobody knows. That means the muon neutrinos are less in the atmospheric neutrino flux. So how to detect the number of muon neutrinos and number of electron neutrinos? Here we can use our Cherenkov radiation. Now neutrinos, being electrically neutron particle, cannot emit Cherenkov radiation inside water Cherenkov detectors. A neutrino can, however, interact with nucleus inside the detector via W exchange to produce a charged lepton and hadronic jets. Because in the final state we will have quarks which undergo strong interaction, which will form hadronic jets. A neutrino can also interact with nucleus via jet boson exchange. That is the neutral current. So charged leptons having significant sufficiently high velocities produced by W exchange can be detected by Cherenkov detectors. Now Cherenkov rings, a neutrino can interact with atomic nuclei to produce charged leptons which emit Cherenkov radiation. This pattern can be used to infer direction, energy and flavor. How to get direction? If we look at the orientation of the detector, plane of the detector with respect to the cone, then we will get a conic section. It can be a circle or it can be other conic sections such as an ellipse, which will give me the direction information. While with the energy information, for high energy particles this angle will be large. That means the radius of the ring will be large. That means the radius of the ring will give me information on energy and also flavor. Why flavor? Because suppose it's a muon, then muon will get less scattered, whereas electron will get scattered more. So that means electron ring will give me a diffused ring and a muon ring will give me a sharp ring. So here is a diffused ring caused by an electron. This is a sharp ring caused by a muon. So that way we can have information on the direction, energy and flavor of the neutrinos. Finally, some references. Reference of J.V. Jelly, 1958, S.N. Ghoshal, 1994, also Jackson's classic book. This also has a figure which I have used in this talk. And papers, this is the classic paper Cherenkov, 1934. Even before Cherenkov, there are some papers which discusses this phenomena. Heaviside, 1889, and Mallet wrote 3 papers, 1926 to 1928. So I suppose you have enjoyed this talk on Cherenkov radiation, and thank you for watching.